today's session sponsor, Shrinergy. Shrinergy provides solar generators that is the most powerful solar generator, yet still only weighing 20 pounds, capable of satisfying the demanding needs of camp trailers and home appliances for days at a time. This generator is versatile as it is powerful, and for the ultimate in emergency power or camping luxury without the hassles of traditional fuel-powered generators. The kit comes with all solar panel cables you need to get started, plus a wall charger. Connect with the SolarStorm 100 panel and fully recharge the solar generators within 15 hours of ideal sunlight. As you can see here, some of the quick recharge times: 2 to 24 hours with the panels, 4 to 8 with the plug, and then 4 to 6 from the car. And these are just some of the examples of charge times for some of the different various devices that you might plug in. You can see a refrigerator up to 33 hours of life on an Energy Star certified refrigerator. So check those out. And then going one step further, if your clients want to take it to the extreme, the Shrinergy has years of experience in renewable energy industry and has developed a solar microgrid kit with lithium-ion-based battery storage for the U.S., Caribbean, Central, and South American market based on the highest quality photovoltaic panels and hybrid inverter technology as available in the industry. Their kit provides rugged durability, long life, reliable performance, day in and day out for providing solar backup energy for all of your clients' needs. So make sure to check them out over at shrinergy.com. All right, well, welcome everybody to Passive Solar Design and Online Tools for Window Shading Design and Analysis, along with LEED. This course is approved for 1 hour in continuing education units. LEED AP Homes, AIBD, Nary Green, Certified Green Professional, Certified Green Home Professional, and Building Performance Institute non-whole house CEUs, as well as AIA Health, Welfare, and Safety, which may make it applicable for your local state-based design or contractor license. Today I'll be your moderator. My name is Brett Little, and I am the Executive Director here at the nonprofit, the Green Home Institute. So for this session, we're going to be talking about how to get passive solar design right in the first place, tools that can be used to do that, and how that can be incorporated into the benefits of energy and atmosphere points under LEED, BD+C version 4 certification for homes. And joining us to discuss this today is Christopher Gronvik. He is the proprietary of Sustainable by Design, a small business in Seattle, Washington, founded in 1998. Chris is a freelance consultant in the renewable energy and green building fields and has taught green building design and solar energy courses at the college level and for a national green building certification program. Christopher serves as Technical Information Director at the International Institute for Energy Conservation in the early 90s and was the co-founder of the Center for Renewable Energy and Sustainable Technology and has served in many leadership positions for nonprofit organizations within the sustainable energy field. So Chris, we're real excited to have you, and please go ahead and take it away.
Hey, thanks so much, Brett, and thanks everybody for being here. Windows are a favorite subject of mine just because it seems that in passive solar design, it's the one thing that people need to focus on the most. You kind of get your best bang for your buck working with Windows for a lot of reasons. It's something that everyone wants a lot of in their home because it's the only way you're going to see in or out of it. And it is a lot more energy interactive between the home and the environment, mostly due to the fact that Windows generally insulate, obviously, a whole lot less well than walls. And it's the main way that sunlight's going to get into the house. So not going to spend a lot of time on that because I think anyone who's here today understands the importance of Windows. But just if we look at the impact of Windows either on a single home or on a larger scale, we see that even something as trivial as one component of Windows, which is an overhang shade on them, can make a pretty big difference. So a window, especially if it's facing south in the northern hemisphere, can have kilowatts of energy going in or out of it, both conductively or through solar radiation. So when we're doing passive solar design, probably if I had clients focus on getting one thing right, whether that's a residential building, larger multifamily or commercial buildings, it's getting your windows right, and probably the most important part of getting windows right is having the right number of them at the right orientations, and then getting the shading right. And there are a lot of ways you can shade a window, static, dynamic, and other things. I want to focus on one thing today, and that's simple, static overhangs above windows. And on a single home, just getting shading right compared to not doing shading probably saves, $20, $30, $40 a month in energy bills, depending on the climate you're in. And that's not a lot until you look at the fact that you're making one design decision early on in the home's construction, and for the entire lifetime of the home, that's going to be the overhang on your windows. So the $25 a month translates to $10,000 to $20,000 of energy savings by getting the shading right for a single home. And at the national level, you'll see, if we look at, there's probably, I don't know, 1 billion south-facing windows in the United States, probably a pretty difficult thing to count. But if we just take 10% of those that would be things we could put overhangs on pretty easily, you can see that you're saving thousands and thousands of megawatts of energy generating capacity. And in general, I think that building some overhangs is probably a better solution to addressing energy challenges than building lots and lots of new power plants. So we're going to focus on energy today, but just the last point is that there are some kind of more subjective benefits to getting overhangs right on windows, and that's that a well-shaded window is going to make the interior spaces a whole lot more comfortable for the occupants. The last thing you want is to sit in your living room in August and have the sun beating down on you. So we're going to focus on energy today, but there are a lot of kind of auxiliary benefits to getting your windows right in the home, both with overhangs and with other shading devices. So jumping right into it, overhangs have a pretty obvious advantage over certain other kinds of shading, which we'll talk about, and that's that they're a static building element that we just have to build once. They don't involve anything complicated with moving parts, with movable shades, shutters, things like that. They tend to be something that occupants don't need to mess with, which is a pretty good thing because occupants are not always good at dealing with anything that's dynamic that they have to maintain or change daily or seasonally. And another nice thing about overhangs is that they're pretty close to optimal for the seasonal changes of the sun's position. Now, when we look at the problems with overhangs, it's that they aren't quite optimized for that, and that's going to be a lot of what we're talking about today. Overhangs can get you pretty close to providing shade when you want it and sun exposure when you want it, but they're not perfect due to some challenges that are just plainly physical, and that's really what we're going to talk about next. Another big challenge with overhangs is sometimes the optimal overhang is very difficult to manifest in construction. So you can come up with a theoretical design, this window needs this overhang at this height, but it's not always going to work with a specific building project. So overhangs in one sense are very simple. You can do some calculations. You can probably come up with what, from an energy perspective, is an ideal overhang. But in the real world, you're faced with all these challenges like your clients and the structural and aesthetic and financial aspects of the project. So as a designer, as an architect, as a home builder, as a consultant, it really is an art because you're balancing all these things. And there's the optimum shading system you'd like for building. There's all the real life stuff. There's all the other interaction with the heating, ventilation, air conditioning, the project economics. And so a experienced professional is going to have to take all these factors and work with a client and come up with a design that kind of balances all of them. The biggest challenge with overhangs is going to be the difference between where the sun is and what the temperature is, and that's the seasonal energy lag. So I'm going to choose St. Louis just because it's in the middle of the country. I don't think I've been there in 30 years, but it has a moderate but balanced and kind of representative climate for the United States. If we look at the daily temperatures, this is the average of the daily high and low in St. Louis. We see that, as is typical in much of this country, it starts to get warm in early summer, it stays really warm through August, and starts to cool off a bit in September. So those are months where cooling is required to bring down the interior temperature to something that's comfortable for occupants. We see it in the wintertime, it starts getting cold in November, it stays cold through March, and April is kind of a shoulder month where some heating is required. So here we've just labeled as cooling any months where the average temperature is 75 degrees or more, and as heating, any months where the temperature is 50 degrees or less. So if we take the summer solstice, right around June 21st, that's kind of the point where the sun is the highest in the sky during the day, and on both sides of that, it's going to be mirrored. So in June, the sun is in a certain place, but on 1 month on either side of that, in May and July, the sun's in the same place. In April and August, the sun's in the same place. So here we see, just graphically, in St. Louis, the sun at noon, at solar noon in June, is at about a 75-degree altitude angle. Then way down in December, it's at about a 28-degree altitude angle. So it's a pretty big swing, and the point of an overhang is to take advantage of the fact that the sun is higher in the sky at the points where we generally want to have a little bit of cooling. So if we put an overhang on that window, this is just kind of a schematic representation, we see that during March and September, the sun follows the exact same path through the sky. And that is the big challenge with the seasonal energy lag, because here we have the heating and cooling season of St. Louis mirrored around the summer solstice. The overhang is in the fixed place, and in March and September we see about a 25-degree difference in daily average temperature. But this overhang is providing the exact same amount of shade. So that, while an overhang gets you pretty close to shade in the summer, sun exposure in the winter, the biggest challenge is about a month-and-a-half difference between the sun's highest point in the sky in a temperate climate and the warmest time of year. And that's just the physical property of the thermal capacitance of the land and the water, so that there is a 1 to 2 month lag of heating and cooling behind the position of the sun. And that imperfection means that you're always going to have to make some balances and some compromises when designing a window overhang. And we'll see that right around the summer solstice, you're going to be fine because you're not going to need a lot of cooling, or if you are, the sun's going to be high in the sky. Right around the winter solstice, December, January, you're going to get good sun exposure. It's those shoulder months, March and September, February and October, April and August, where the sun's in the same place, but you want to heat in one part of the year and cool in the other part of the year. So when we design an overhang, the first thing we need to do is figure out the whole context, because in general, we're going to want to have a little bit of a bias towards sun or a little bit of a bias towards shade. And that's going to depend on the climate you're in, how extreme it is, whether it's a heating or cooling climate. If you are in northern Minnesota, you're almost certainly going to want to have a bias toward getting as much sunlight as possible, as much heat. If you're in the Southwest or the Deep South, you're going to want to bias toward as much shade as possible. So as an architect or designer, figuring out what's your climate, what are my building needs, what do I have for heating and cooling? If you don't have an air conditioner, you're going to want a little bit more of a bias toward making sure you don't put too much heat load on the building, even at the expense of not quite as much heat in the winter as you'd like. The glazing configuration is pretty important, making sure you have as many windows facing the right directions. Most people are going to say you want at least half your windows facing south. Again, that really depends on the kind of building you have and the climate you're in. And here we're mostly talking about residential, small commercial buildings. Everything is pretty darn different once you get into large commercial building design like skyscrapers. So but those don't tend to have overhangs. So we're just going to kind of focus on small residential buildings where we're looking at 10 or 20 or 30 windows, which we're trying to balance here. And finally, occupancy. What are the spaces used for? And ideally, the window overhang design is addressed early in the process, and the building and the occupancy needs, those are all part of the design process holistically from the very beginning. In real life, I tend to find that people start looking at window selection and shading pretty late in the process, and it's too bad. And it means that a lot of opportunities were lost early on, but you usually just have to live with it and say, all right, we've already decided that the bedroom goes here. We decided that we're having these view windows to the south, and we have all these wonderful windows to the west to look at the mountains or whatever, and you're left with just a lot of design challenges. So ideally, you're going to address as many of these things and mitigate a lot of the problems with getting your building morphology right, getting your window glazings in the right place, but you're almost always going to have to do a little bit of cleanup work and say, all right, here's where we are in the building design process toward the end. We're going to want a whole lot more heat gain in this building, or we're going to want a whole lot of shade in this building, depending on kind of where you are in that process. And that's where you may need to use overhangs to provide as much shade as possible in a certain climate or building, or be able to back off a little bit and say, hey, we don't have that much problem with solar heat gain. We can afford to have a little bit of a bias toward extra heat gain and not need quite as much shade. So when you're looking at designing overhangs, there's kind of different scales and approaches. The easiest is to use a rule of thumb, and there's plenty out there. I mean, most houses are designed with overhangs that are either accidental, non-existent, or someone just says, an overhang is probably a good idea, I'm going to put one on this window. So if you look at the existing inventory of windows and overhangs, they tend to have not very many of them, and they're kind of arbitrary. And fortunately, there's been a lot more consciousness of the importance of passive solar design lately, and so there's a lot more intention put into it. The certification programs, the education, these have all meant that for at least some portion of the inventory of homes, there's been a lot more intent on getting windows and getting shading right. And getting it right with a rule of thumb means looking at something like a diagram that says, oh, an overhang needs to block all of the sun on June 21st. It needs to admit all of the sun on December 21. So that's probably the most common rule of thumb that's out there, and I believe that's part of the current LEED standard for the energy and atmosphere credit for passive solar design. So that's, if you look at passive solar design books and guidelines from the last 20 or 30 years, most of them are going to say that's how you design an overhang, and we'll look at an example of that in just a little bit. If you want to get more detailed, you can use an analytical tool, which is what we're going to talk about today, which takes a little bit more time than doing a rule of thumb, although not necessarily, and it just means putting in actual data about your climate and your window and looking at what the impacts are of a proposed overhang, and then adjusting the dimensions to kind of tune the shade and the sun exposure to get closer to what you think might be appropriate for your building or for your climate or your project. Finally, you can go all the way into energy modeling, and that's been something which has been inaccessible for small projects most of the time. If you're going to build a skyscraper or a large housing development with a lot of units, a multifamily, it may make sense to spend $10,000 or $20,000 historically on energy modeling and get those things right. Even though, because people who build the things don't tend to pay the energy bills, that hasn't even been very common throughout history. But fortunately, the energy modeling has gotten a lot more accessible, a lot more affordable, and I think Brent was mentioning that the upcoming changes to LEED are going to involve using a more energy modeling approach. And I don't know the details of Remrate, of what they do for shading design, but hopefully this means that there's going to be a little bit more data-driven decision-making when it comes to looking at windows and looking at shading. So today we're just going to look at analytical tools that can be used for overhangs. I have a number of tools on my website that involve windows. Some of them are more for sun position, some of them are more for climate, but this is a list of some of the tools I have for doing overhang design. And if we wanted to see what one window, the impact of an overhang on one window, and see what it looks like at a given date and time, there's the window overhang design tool. And this is pretty simple. This is a graphic of a window and a graphic of an overhang above it and a bunch of sliders. And you can set the sliders to where you are, when you are, and where your window is facing and how big it is. So taking St. Louis, if we want to see take a hot time of year, this is mid-August afternoon. We have a window facing south, and we're just going to say, what happens if we put an overhang about 18 inches above the window that extends about 3 feet out from the window facade? What's that look like? So if we just take the sliders and set the latitude, date, and time, set where the window faces, put its size, and set the dimensions of the overhang, you'll see that there's your window, there's your overhang, and it's about 60 or 70% covered in shade. Now you can just move the sliders back and forth, and it's like a what-if scenario. What if my overhang were wider, because I'm going to shade the windows with the eaves of the house? What if the window were little bit less under the overhang and just move the overhang closer to the window, we're going to improve our shading. What if the overhang is only as wide as the window? What's that look like? So a tool like this is pretty good for doing a quick visual representation of the instantaneous shade on the window from a specific overhang. And this is cool unless you're trying to look at a whole bunch of windows for the entire year, in which case you need a tool that helps you visualize what it looks like on a larger time scale. So the second tool that I have on my website looks at an annual analysis of a window overhang. The Overhang Annual Analysis tool also takes as inputs your latitude, the direction the window faces, and it takes the window overhang dimensions into account. And then it has a little matrix below it that has the entire year represented. So the rows of that matrix are the months of the year. The times go across left to right from morning through afternoon. So if we were to take the data for St. Louis and the overhang we were talking about and enter it here, so there's St. Louis's latitude with a south-facing window. We have a 3-foot by 5-foot window with a 3-foot overhang 18 inches above the window. Hit calculate, and this shows you throughout the entire year what the shading is on that window. The green squares, the light green squares, are when the sun is below the horizon. The blue squares are for when the sun is above the horizon, but it's behind the window, not shining on that facade. And obviously, all of the data there shows you the percent shading throughout the year. So if we take the current month, I think we are in February by now, we see that between 7 a.m. at sunrise and 5 p.m. in the afternoon at sunset in St. Louis, we get just a little bit of shade, primarily concentrated right around noon, where we peak with about 20% of the window getting some shade. As expected, this is mirrored around the summer solstice and winter solstice, and we get a whole lot more shade in the summertime than we do in the wintertime. But what if you said we want more shade than that? If we take the exact same parameters and make the overhang longer, move it closer to the window, we see now we get a lot more shade. September went from, on the last slide, September was about half shaded. By making the overhang longer and closer to the window, we see now September is completely shaded. So this is just a way to see kind of a what-if scenario. What if we want a lot less shade on that window for some reason? Now the overhang is shorter, it's moved above the window a little bit, and we still get some summer shade, but you're going to see some problems in that window in the late summer. So now we're looking at August, the window's only about half shaded at noon. On the plus side, we have very, very good sun exposure in the wintertime. So if for some reason that were your priority, an overhang that's both shorter and further above the window probably gets you closer to what you'd like. So doing a more specific example, let's say that we have a house in St. Louis and we're trying to design it without an auxiliary cooling system. So our bias is for more shade. This is actually pretty common, not just not having an air conditioner, but needing more shade. People like windows, and very, very, very few homes get to the point where, wow, you need more heat gain. The vast majority of homes that are designed are going to benefit from a little bit more shade, a bias toward shade with the overhang. And that's not just because of their climate, it's often because it's a little bit more comfortable to be in a house that's not overheated. If it's a little cool, it's easy to add heat, it's easy to put on clothes, it's a little harder to take off clothes and to remove heat. So the majority of homes where you start to pay attention to shading are going to want a little bit more of a bias toward shading. So we're going to take an example of St. Louis, and let's remind ourselves of the climate here. We have 3 months where cooling is a high priority, and if we're really trying to provide shading, even getting into September, we're going to want to create some. September has plenty of 85-degree days in St. Louis, especially early in the month. And at that point, if you're getting 2/3 of your windows with sun exposure and it's 85 degrees, you're kind of living in a greenhouse. So let's see if we can design an overhang that's going to really focus on providing definite shade in the first part of the summer, June, July, August, and kind of as much shade as possible in September. So if we first look at the rule of thumb we were talking about earlier, this is a schematic representation. You'll see this in the LEED documentation, almost this exact diagram. You'll see this in a lot of passive solar design books. we've taken a window, we've drawn a line from the bottom of the window at the summer solstice noon sun angle. Again, that's 75 degrees for St. Louis. And we've taken a line from the top of the window, we've drawn that at the winter sun angle, which is about 28 degrees for St. Louis. We connect those two lines, and that's where we locate the lower outer edge of the overhang. And this is probably the most common method that's used out there. And if we use this design for St. Louis, we find doing a bunch of trigonometry, so this rule of thumb is actually not that much easier to use than an analytical tool. If you do some of that trigonometry, you'll find that your overhang ends up about 18 inches deep, about 10 inches above the window. So if you enter those dimensions in feet in the overhang dimensions in the upper right of this diagram and hit calculate, you'll see that the shading is represented below. You do get pretty good shading in June. You start to see some sun in July hitting the window. August, the window around noon is about half shaded. In September, it's about 1/4 shaded. So using this rule of thumb, it sure is better than no overhang at all, but you can see here pretty obviously that when it's 90 degrees in August and you have several hundred square feet of windows and they're only half shaded, you're going to have a pretty significant overheating challenge in that home.
Hey, and Chris, I just wanted to help clarify for a comment that came in.
Yes.
When you say a bias towards more shading, you are specifically talking about shading that is hitting and coming into the house and not shading that's hitting the roof line. And the reason I say that is somebody was concerned because they were saying, well, we want as much sun as we can if we're putting, active solar on our house.
Right. Oh, yeah, that's correct. So we're really just focused on shading these windows, and there wouldn't be any byproduct of that shade shading any other part of the house, including the roof. Correct. Yep. But it's a good question because there's always going to be that balance. Sometimes you want shade, sometimes you don't. And when you get into, I guess if you're doing active solar, since that's almost always going to be up on the roof, there shouldn't be any interaction with any shading that you're looking at for windows that are on a vertical facade of the house. So, if we take the exact same scenario and we want to come up with an overhang that's not just the rule of thumb, or maybe this is just another version of the rule of thumb, I have a super quick overhang recommendation tool that helps you at least get a place to start with window overhangs. It's pretty simple. There's one input, and that is how high is your window? What's the height of the glazed area of your window? And you enter that, and it will tell you at different latitudes for different climate types, what's the ratio of the overhang to the window that's probably a pretty good place to start to meet your needs. This is just, again, it's very, very, very simple, but if I have a 5-foot tall window, St. Louis is a mixed climate for sure because you have heating and cooling. The closest latitude in this chart is 40 degrees to St. Louis, which is at about 39. So if I cross-reference 40 degrees latitude with a middle column of mixed, with a 5-foot window, I see a pretty good place to start is an overhang that's 3 feet deep, that's 1.5 feet above the window. So already that's an overhang that's twice as high and twice as deep as the previous rule of thumb. So if I take that overhang and I enter it into the overhang annual analysis tool and hit calculate, you'll see that we get a little bit more shade than we did and a little bit more than the example before. That's just a bigger overhang. And we can see that in June, July, and August, we now have 100% shading, and in September, we have about 50% shading. So looking at our priorities for this example project of getting more shade, we see that in August, we've really changed the shading from half to full. In September, we're seeing a lot more shading. This is just a place to start this recommendation. You could say, I really want to have even more shade in this project because it's very problematic to get that much sun even in September in this climate with my project. So I could say, what if I make it a little bit longer and a little bit closer to the house? It's not that hard to take this and adjust it a little bit to get even more shade in the project, or even take it one more step. And now I can get almost complete September shade, but now you're really starting to impact your winter sun exposure. you've got an overhang that's almost as deep as your window, which might present structural challenges. It might definitely present aesthetic challenges. So again, this is a balance. You can really take this to an extreme and really tune this to get it where you want, but you're going to have other important factors in your project. If we do a side-by-side comparison, here's the shading output for the St. Louis example with the rule of thumb that's used by LEED and others on the top, and using the simple overhang recommendation of 3 feet and 1.5 feet down below. And it's not like it's incredibly different, but if you do look at July, August, September, you do see that you're getting, especially August, this would be a very substantial difference in the house, having the windows half shaded or completely shaded in August, just from a comfort perspective, and if you had an air conditioner, from an energy and economic perspective.
Chris, there's a question. Is there special consideration included for a greenhouse window which extends 1 foot from the vertical surface of the wall?
So is this a window that sticks out that's connected to the house, or that's thermally decoupled from the house?
I guess we'll let them answer and we'll keep moving.
Okay, yeah, just let me know. Yeah, I mean, obviously, this is a very simplified example, which is just a vertical window on a vertical facade. As soon as you start getting into more complex situations of windows facing other directions, of different types of windows that aren't vertical, skylights, you know, a greenhouse that's disconnected from the house a little bit, those start getting into a little bit different considerations. But fortunately, the vast majority of windows are pretty simple rectangular things on vertical walls, so it's usually you can use tools like this. If we look at these two examples of taking 8 windows, 3 foot by 5 foot, using a rule of thumb to do the design and just doing a little bit of a tweak to the design using these recommendations, visually this is what it looks like. If we look at it energy-wise, there's a difference on an annual basis of about 100 kilowatt hours of excess solar gain per square meter of window area. And I think we're going to have time to chat about that toward the end of this call, but there are some tools available to calculate that as well. All I did is look up the overhang, those 2 overhang scenarios, and look at how much heat gets into the windows. And again, it's 100 kilowatt hours per meter squared of glazed area, or about 1,200 kilowatt hours a year of excess heat is getting in due to the difference between those 2 overhangs, the rule of thumb and one that's a little bit deeper and above the window. So if you don't have an air conditioner, you can just think of that as 1,200 kilowatt hours of heat that makes your life a little less comfortable. If you do have an air conditioner, you're probably going to save yourself $30 to $50 in air conditioning bills by not having that excess heat. Compared to no overhang, it's a pretty big difference. It's a couple $100 a year or more, but just the difference between these 2 dimensions of overhang is about $40 a year in air conditioning difference. And not huge, but again, over the lifetime of the house, it's a couple $1,000s. And when you're doing passive solar design, when you're doing green buildings, there's a lot of little decisions to make. Every window, overhang, wall component, all the parts of the building. A successful passive solar building, a successful green building is simply a series of a lot of very good decisions being made at an integrated level. And so window overhangs are this is just south window overhangs, one orientation, one element of one part of the design, and it's $2,000 a year in savings. The idea is that if you could get all the elements of a building right, these add up to tens and tens of thousands of dollars of savings, so pretty significant. Do we have the question, Brett? Did you get a clarification on that so we can answer that before we move on?
Yeah, it was connected.
Okay. Yeah, so if you have, I don't know exactly what that is, but if you have a window that bumps out a little bit, I guess you would just have to think of that as the plane of the windows, the facade, and measure the overhang relative to whatever plane the window is in. I've seen kind of greenhouse windows similar to bay windows that bump out from the house a little bit, and those you just have to look at as a series of windows facing different directions and look at how you shade all of them. Obviously, one of the big challenges with overhangs is they're really good in temperate climates for equator-facing windows. They are obviously a lot less effective once you start facing further east or further west, simply because the sun's spending a lot less time high in the sky. And you get a lot less of a difference between winter and summer with sun position. And what makes overhangs work is the seasonal difference in solar elevation angle. And so when you get something like a greenhouse window that bumps out, that can be very problematic to shade if there are kind of east and west facing windows as part of that glazing component. Are there any other questions about that before we jump into a brief discussion about calculating heat gain?
No, I don't see any.
Okay. So the overhang annual analysis tool looks at direct sunlight that's coming into a window and how much that window is going to be shaded. I have a very related tool that's simply a version of it that is still a little bit under development, but it has two changes from the original overhang design. Its purpose is still to help you optimize an overhang. You still input information about your climate, your window, the overhang dimensions, but it has output that differs in a couple of little ways if it's useful to people. So the first, when we were calculating this before, we were just looking at direct sun. So we can leave, this is the beta version of the tool, that's the new one, and we can leave this set to direct sunlight only with the same overhang dimensions as before, and the outputs look identical to what we had earlier. So we get shade throughout the summer. We're about half shaded in September, and this is just looking at what's the impact, assuming all of the radiation from the sun is coming directly from the sun. The point of this tool is to improve the accuracy of that calculation. So we can more accurately, if we're trying to get a little more precise, look at the sun that's coming in through a window through three different means. The direct sun, which is just the direct radiation coming from the sun, the diffuse radiation, so what's coming from the sky, so the sky is going to both reflect, reabsorb, and retransmit radiation, so that is a non-trivial part of solar radiation, and it doesn't just come from the sun, and then reflected off the ground. So if you take this tool and change it from direct sun to direct and diffuse and reflected, you can see how much the outputs change. So here's what it looks like with direct sun. Here in the summer, you're getting 100% shading. In the winter, you get 100% exposure. But more accurately is to look at what's the total solar radiation coming into that window from all sources. And this simply breaks up the solar radiation into those three components and analyzes them independently. And we'll see that in the summer, sure, you are getting some shade, but you're not getting 100% shade. You're getting 62% shade or 56% shade, and that's simply because the overhang does a wonderful job at preventing all direct sunlight from getting in, but almost half of the solar radiation gain in the summertime is not from the sun direct light, it's from the sky, which the overhang provides only partial shade from. One reason it's a big difference in the summertime is that when the sun is really high in the sky, two things happen. First of all, the window has a small cross-section compared to the sun. So imagine the sun's 75 degrees up in the sky, the window kind of looks effectively skinnier to the sun than if the sun were lower in the sky. So a smaller percentage of the incoming radiation is from the sun at high sun angles, whereas the sky looks the same to the window all the time. The other factor is that when the sun is high in the sky, it's at a very oblique angle to the glass, and as soon as the sun gets to about a 70% angle to the glass starts getting very reflective, and by the time the sun's at 80 degrees, glass is almost like a mirror. So it's just a little bit more accurate to look at the total physical picture of the different types of solar radiation, and it does make overhangs look a little bit less effective, but just accurately, that's what they are. And so the purpose of this tool is to provide a little bit more scientifically accurate data and bring that into the conversation. The other thing this tool will do is it will let you look at the heat gain coming through the window, not just the shading. So here we're looking at the amount of window that's shaded. Here, the tool is calculating in the kilowatt hours per meter squared of glazing how much energy is getting through that window. And in the end, this is the most accurate thing to do when you're looking at what is the energy and economic impact of a window overhang. And this was really the impetus for me to design this more accurate version of the tool. It's accurate by taking the different components of solar radiation into account, and it's accurate by not just thinking about the light, but in the actual thermal load that that solar gain is putting on the house. And as we can see here, it's pretty good. So in the summer, we're just looking at a few kilowatt hours per month at that hour that's getting through the window, whereas in the wintertime, you're looking at values that are 7 or 8 times higher. So this overhang, you can see, makes a pretty big impact in the house, getting you almost an order of magnitude more solar gain in the wintertime when you want it than the summertime when you don't. So ignoring the seasonal energy lag, this is a pretty effective thing. The seasonal energy lag means as a designer, as an architect, as a home builder, you're the one responsible for taking that into account and balancing that overhang with all of the other components. Were there any questions about the beta version of it?
No specific questions. No specific questions there, but you know, I mean, maybe you want to get to this later, but you know, somebody was trying to determine the trade-off of using passive solar to heat versus active solar, considering insulation up in a cold weather climate, and you know, maybe what kind of thoughts you have on that, or if there's even a trade-off at all.
Right. I mean, active solar, I mean, both passive and active solar describe a whole suite of technologies, building components, and strategies, but in general, passive solar has the advantage that it's something you just kind of build once, and it's elements of a building that you have to do. I mean, you have to put in walls and windows, and passive solar is just manipulating those components to optimize them for, you know, energy, comfort, and all these things. Active solar tends to be something you add on to a house that is more it's an addition. It's not something that's already there. Depending on what you mean by active solar, it can have moving parts and be more expensive up front and have maintenance. On the other hand, it's something you have a lot more control over. If you had some kind of an active solar device or system on your roof, you could tie into that when you wanted to. So it's something you have more control over, and you're not going to be affected by the seasonal energy lag that comes with a static, you know, unchanging passive solar element like an overhang. So it kind of depends on your tolerance for complexity and your budget, you know, what mix of passive and active solar are going to make the most sense for you.
Would it be fair to say that starting out with design with passive solar in mind gets you maybe closer to a project that's sort of on track to be ready for active solar in some ways?
Absolutely. I mean, think of it as building a solid foundation for a building. You know, you work with things that are higher impact and more fundamental and simpler first, get things as close as you can, and then use technologies, you know, the heating and cooling and active solar, all the things that are more expensive, complicated, and require maintenance, use those to fine-tune things. You know, it wouldn't make any sense to have a building that gets passive solar completely wrong and then try and fix that with some appliances. So it's, you know, definitely the whole thing about green building is just this kind of pyramid where, you know, it's almost like how you build a building from the foundation first, then the structure, then the outside, then the design details. The design process mirrors that. You know, you start with analyzing your climate and your needs and just the site, and you just get smaller and smaller. You start with the site, then the footprint, then the orientation, then the building itself, and then the rooms, and then you start working on things like what kind of window do I need, how do I shade it. So, you know, the design processes that work the best are the ones that think about the long term, that think about the details from the start, but start with the bigger things first, getting smaller and smaller so you get a solid foundation for your project. Don't find yourself, you know, a month away from construction and realizing that your building's facing the wrong way.
Well, we got a lot of questions coming in. I want to ask one of these and then ask everybody. Maybe we can roll through a few more things and then get to the Q&A process if that's okay. And this is one specific to what you were just talking about. If almost half the solar energy comes through diffuse, then what is the impact of the overhang?
Well, a couple of things. First of all, it depends on the time of year, but the overhang does two things. It does address the, you know, approximately 50 to 70% of the annual energy that comes from direct beam. So it does address the largest component of it. And it does shade the window from some of that diffuse light also. And, you know, in some ideal world, the overhang could be completely effective in shading a window, but it's not. And about probably almost a third of the energy that comes in through a window is not addressed by an overhang just because it's the sky and it's out in front of the window all the time. And so, you know, somewhere between probably maybe a quarter and a third of that energy, that solar radiation, is not addressed by the overhang. So think of the overhang as a great way to address the largest component of incoming solar radiation and most of the comfort and glare problems. So not too many people have a problem with the sky, you know, providing discomfort and glare, but direct sunlight shining into a window right on you is not comfortable. So an overhang is not the only strategy. When it doesn't work, when there's, you know, a west-facing window, when there's a lot of south-facing glass because it's your view and that diffuse light even is too much, then you have to start looking at other solar gain mitigation technologies, whether that's blinds, you know, windows with a low solar heat gain coefficient, et cetera. You know, then you get into the balance of windows that have too low of a solar heat gain coefficient for the window gain that you want, or you get into movable blinds. Now you're relying on the occupants to get things right to make the energy design work. So that's kind of where the balance comes in, and that's why it's important that design professionals understand how windows and overhangs work, but what all of the other, you know, energy flows are and how we address them in a building.
Great, thanks. So let's wrap up the presentation, and we got a lot of great questions. We'll get to those when we get through it.
Okay. Yeah, that's all I have. I think you were going to talk a bit about LEED.
Oh, perfect. Yeah, I didn't realize we were there. So,
yep.
yeah, I just want to make sure we cover some of the LEED stuff here, and then we're going to get to your questions right away. Building orientation for passive solar. This is a LEED V4 prescriptive pathway credit. So if you're not taking the performance pathway, you can be sure to pick up your solar orientation credits within this section here. And so, you know, some of the things to look at is, you know, ensuring that you meet some of these goals here. And so all of the different tools that Chris presented that are available and open source, I believe, are all different tools that can help you hit some of these bare minimum thresholds. And so these are sort of the bare minimum that you need to achieve for LEED for homes purposes. Obviously, using some of these other tools that we discussed are going to get you much more in depth and more in detail, but they'll at least give you the data you need to do a preliminary plan review and ensure it's on track for LEED. So obviously, the first step is analyzing the site. So if you have the choice to choose the site that you want, obviously that can make or break solar impact as well, especially if the site is completely shaded out or completely open. And then, of course, you know, there could be requirements in certain lots or certain areas or certain neighborhoods that a house be facing a certain way. And so obviously that can impact you or require you to go and get some kind of waiver or whatever. But knowing what your site is going to be your number one issue, obviously, and knowing the climate, of course. And then step 2, you're going to want to orient the design, orient the house and design openings. And so anywhere in the LEED program, if you read the word south, but you're in the northern, or you're in the southern hemisphere, then you just want to flip that around. So obviously you want to orient. So obviously up here I would say the north-facing glazing area is at least 50%. So you just swap those depending on what latitude you're in. That's going to make a difference there. And then size solar shading. So based on the project's site latitude, use a solar calculator for the appropriate roof overhangs or other shading features on the south side of the house. Alternative shading strategies may include sunshades, natural vegetation, trees, design shading vegetation, such as using like a non-invasive vine system. And then lastly, you want to document compliance. So during the design phase, just being able to document that, and so tools like what Chris presented are going to be able to help you document that that's been done, and then any kind of rater or consultant is going to be able to look at your plans and see that you're within compliance there. And then obviously the green rater is going to be coming out on site, and then just taking a look at the project, measuring it, and again ensuring that it's within compliance of what you put in your plans and your documentation. And then there is other passive solar strategies, so considering incorporating thermal mass, heat absorbing flooring, thermal storage walls, masonry features for winter solar radiation, and all those different items are things that you can take a look at. So project teams whose buildings have views to the east, west, or north should consider design revisions to assist in meeting the criteria for the credit. For example, the addition of a deep porch and well-placed landscape would shield west-facing windows from excessive heat gain and preserve the view. On a north facade, triple-pane windows would allow the large expanse of glass for scenic vistas without compromising energy performance, and experienced architect can help projects meet the criteria for the credit while saving energy and improving that thermal comfort side. So that's the prescriptive pathway. Now, the performance pathway, which is what most project teams use, so that's LEED, BD+C, V4, EA, annual energy use. That's what most project teams use, and under the new LEED V4.1 rating system for homes, the prescriptive pathway will go away entirely, so only performance. So, and in this case, you're going to be working with Remrate and the HERS index rating. Architects can get access to REM Design or Remrate Lite and produce their own preliminary ratings without bringing a rater on board, and so that gives designers or building plus designers the ability to work with some of these different details that exist within Remrate. There is a handout here that everybody should have access to, and that we'll send out a little bit later. That's from Remrate, but it tells you all of the different options. So when you are designing your house, you can put in your window-to-wall ratios, solar heat gain coefficients, window area, orientation, overhangs and shadings, interior shading such as blinds, and adjacent shading details. And you can start tweaking those things and start seeing what your energy load demand is, and then obviously design from there. So if you get this right, then maybe you need a little less insulation. Maybe you need a smaller heating and cooling system. Maybe you need less PV. And so that can all be done in the rest of Remrate, and then that's going to get your HERS index rating, which is going to give you your ultimate LEED score there. So that's all we have here. I see there's a lot of great questions, and before we get to those questions, I just want to again thank all of our members, our board of directors, our volunteers. Huge thanks to our sponsors, GeoComfort, Geothermal Systems, Build Equinox, CERV, Smart Ventilation, Niagara Conservation, lowest flowing toilet on the planet at average 0.6 gallons per flush, Panasonic Ventilation, Certainteed Air Renew Formaldehyde Eating Drywall. For those of you listening live here, make sure to take that survey at the end. Check your spam for the certificate. get your CEUs that way. And for those of you watching this in the future, make sure to take your on-demand 10-question quiz with an 80% passing rate. All right, so a lot of questions piling in here. We got some time for questions. Don't worry, we want to definitely get to as many as we can here. So let me find those. So the first question, Chris, is the heat gain value of a typical latitude for, say, all big cities okay, let me try to read this. Is the heat gain value atypical for the latitude for, say, all big cities at the latitude in the U.S.?
Let's see how to answer. I'm not sure exactly what the question's asking, but ignoring the conductive and convective heat gain, just looking at solar heat gain, if you're at the same latitude, the sun is going to follow the exact same path throughout the year, and you're going to have the exact amount of solar heat gain through the same window if it's at the same latitude, no matter where it is in the world, if that makes sense.
Yeah, and you know, if they want to ask it more, we'll definitely go into more depth there, but thanks.
Okay.
The next question is, do you have a calculator for east and west facing windows with vertical FIN type shading devices on the side?
You would have to use two different tools. First of all, it's a good question. The overhang calculator, the heat gain calculator, all of my calculators are completely independent of hemisphere. I should say they will allow and work for both the north and south hemisphere, and you can have windows facing any direction. I was simply using south facing because it's the most common, but the overhang calculator works perfectly fine for east, west, even north facing windows in the northern hemisphere. I have a vertical fin calculator on my website. It presently does not calculate heat gain, so what you would have to do is calculate the heat gain independently using my overhang tool with no overhang perhaps, and then use the shading tool to figure out how much of that window is shaded and kind of overlay those two. My goal in the next year is to take all these tools I've developed over the last 20 years and better integrate them. And that's just simply a matter of finding the time to do that so that you can take any window with any style of overhang or physical shading device and be able to calculate the instantaneous or annual heat gain. So integrating some of these tools and making them a bit more mobile friendly is one of my goals for 2018, 2019, and that would probably make it easier to figure out the heat gain with vertical fins. But for now, you can at least analyze those different components of it and kind of figure it out yourself.
What about foliage plants? Do you have any ability for anybody to view those within your tools?
No, for a couple different reasons. One is it's complicated. Windows are rectangular and overhangs are rectangular, and it's complicated enough three-dimensional trigonometry using just rectangular shapes. You throw up a tree into the mix, and it gets a little bit harder to figure out exactly what's going on and to quantify it, especially as the tree grows and has different seasonal foliage. The other thing is that I find it's not usually a very good strategy. And just like with overhangs, the challenge is a seasonal lag. If you stick a tree in front of your south-facing window, hoping that it gives you shade at the right time when it has foliage, there's two things. It's at the wrong time usually, and it's also providing usually the wrong amount of shade. So, plant a big oak tree just south of your window, and you'll find that even in the winter with all of the leaves gone, you're blocking over half the light with just the branches. So foliage, although you'll see it in lists of design strategies, it is very, very, very hard to get right. If you're just trying to provide shade, like you have a west-facing window that you need to have for some reason, yeah, sure, your focus is on shading that window and then plant some trees and bushes, but for south-facing windows where you want to fine-tune when you're getting solar gain, foliage is something which is often not an option, and if you do use it, it's a challenge to get it anywhere close to right.
Great, thanks. There was a question here on Remrate tool that I just wanted to clarify to make sure everybody understood. And just to clarify, the Remrate program, which powers the HERS index rating, home energy score rating, which we have a whole full-hour session dedicated to that, so you can check that out. But to be sure, that tool does not do any good for LEED, BD+C, or LEED commercial. It's only applicable to LEED, BD+C V4 homes, and not even to LEED home mid-rise either. So, and so just to be sure, it's not something that can assist on a commercial project. Certainly could maybe give you some good design strategies on a small commercial building. However, it can't be used as the energy pathway to certify that building. Chris, assuming you know what this is, the question is there a way to minimize the breathing feedback?
The what?
You know what? Never mind. I don't
that's
think that was a question.
Right. I think I know what that means, yes.
Yeah, it took me a second and then I heard it, so never mind. Right. Everything's fine on my end. So I've got a couple questions before we wrap up here. It doesn't look like there's any more. I want to kind of move into the larger buildings if you have any insight into those. My understanding is that even up here in cold weather climates, larger multifamily buildings usually always have cooling loads, even in the wintertime. That's the biggest problem. Do you have any recommendations for those types of buildings, just off the cuff, as far as, you know, even just working with the sun and not being impacted by it as much?
Right. Yeah, so physically what's going on is as a building gets larger, its volume is expanding at a cubic rate and its surface area only at a square rate. So you get a much smaller surface area to volume ratio with a large building, meaning you're generating a whole lot more internal heat with a lot fewer pathways for that heat to get out to the outdoors. So, you know, if you went to the North Pole and built a skyscraper, you'd be cooling it just because it has so much internal load, heat gain, and heat production. So for a large building, you are always going to be focused on shading, and not just shading, but solar gain mitigation in general. Unfortunately, it's been very sexy for architects to work with glass. So you see a lot of glass skin buildings, and there are a lot of people living and working in large glass buildings where the energy bills are 10 times what they should be, because that building is just one big solar collector at a time when it really is on 24 hours of cooling all year round. And so the key with big buildings is minimize the amount of light that's hitting it through overhangs and then using solar control glazings and exterior blinds to keep as much light off of that building as possible. It's just a whole different design strategy working with larger buildings, and your focus changes from how do I balance the seasonal energy lag of heating and cooling to how do I mitigate solar gain 24/7 in this building. And again, that's for really big buildings. You get down to like a 4-story multifamily building, you're somewhere in the middle. You're going to still have a little bit of a heating season in the winter in some climates, but your bias is clearly going to be towards shading in any building once it starts to get much bigger than a really big residential home.
Great, thanks. And the last question I have is, you know, you had mentioned that once you start incorporating blinds, you're relying on the occupant behavior. However, I thought I've heard of maybe smarter blinds. Do you know of any types of blinds that actually can be programmed to where they're at to, you know, open and shut at certain times of the day to let sun in or keep it out?
Yeah, absolutely. There are some kind of home automation systems that can control blinds, and when you leave the United States and look at places like Japan and parts of Europe, there are a lot more common technologies available for things like motorized shades. One thing that's really hard to find in this country that's a little more common in a few others are exterior shades that work really well, that are, you know, motorized or controlled, you know, shutters and other things. And that really would be ideal. You know, you can put blinds inside of a window, but the sun's already gotten in. And the only interior blinds that are really effective are interior blinds which are highly metallic and can bounce the sun right out back through the glass without changing its wavelength. The biggest problem is even white blinds, if you put them up, the sun is going to be absorbed into those blinds, re-emitted at a longer wavelength, and can't get back out through the glass. It's just the greenhouse effect. So the vast majority of interior blinds don't work very well. So ideal is to have external shading devices so the sun never gets to the glass. The next best thing would be within the 2 panes of glass shades. They make shades that are kind of between the 2 sheets of glass, maybe a little on the technically complex side. Third best is metallized internal shades, and beyond that, you know, use whatever shades you can, but know that the heat is mostly still getting in the house.
Great. Thanks, Chris. Well, that's the end of our session here. Can you just tell people where they can get more information about you, what you're working on, your tools, and how they can help support you?
Yeah, just the Sustainable by Design website is susdesign.com, and that's where my tools are. They haven't all been updated in a long time, so again, one of my goals is just based on all the feedback I've gotten over the years to go ahead and start working on improving these tools. I really think that the vast majority of people, when they're designing a house, want to get these things right. Not everyone is an architect or can afford to hire lots of consultants, so my focus has been on providing free tools for people to use to at least get what I think are the most important aspects of solar design right in the house. So I hope that people can check the tools out. Feedback's always welcome, and look for these tools to be improved over the next couple of years.
Yeah, awesome. Thanks for your time. Thanks, everyone, for joining us. Have a great rest of your week. Take care.
All right. Thanks, Brett. All right.